Interesting question. What happens when I have digital logic gates and digital logic functions, but I only have, say, two input NAND gates? Now, why might this happen? Why might this be a constraint? Because, imagine a typical FPGA, for example, you just write your VHDL or Verilog code and it constructs it for you. Why would I care about this? Well, one, if I happen to be building something out of discrete components, that might make sense, but then you're thinking, but people don't do that much anymore. They actually do more than you think, even now, because there are times when that's just the efficient way to build something. The other place where this comes into play in a big way is if I'm building various digital circuits on a custom ASIC chip. And in those cases, the digital components will probably operate most efficiently in either a NAND or a NOR configuration. And so if I'm saying a NAND configuration is the more optimal because I'm balancing mobilities of the transistors and so on, that's what I would approach. I could also have done the same question with doing everything with NOR gates, flipping over those arguments and so on. It's more just kind of how do you start thinking about this question? So now you begin to say, all right, well, what does that look like? And one of the most important parts is we have these wonderful theorems where we can go from or NOR into and of inverses of things. And I'm going to put it here as being like if I have A or B, it's really the equivalent of the NAND of A inverse and B inverse. And so you can imagine building a NAND gate and building two inverse blocks. So you can start having fun with this. You can say, well, imagine if I have A plus BC. Well, again, that could be done as the product of A bar and BC. Well, that's already a NAND gate, yay. I can do the inverter by basically taking the two inputs of the NAND gate and tying them together. Again, you might go, why just make this inverter? And you're like, well, maybe it matches the timing better. So we're gonna go with this. And then you just sort of finish out the rest of another NAND on the back end. Now, sometimes it's not always that clean. If you sort of say A plus C times B, well, okay, I can certainly do something with the AC part of it and get A inverse, C inverse, and do a NAND, and that's cool. But I still got to deal with the B part and all of this, so what I'm going to basically do is take a NAND and then do another invert to get the rest of the function. And so that kind of gives it to me there. There's a number of other kinds of fun circuits you can do. You can say I've got AB plus B, AC plus BC. And another way to look at that is I go, oh, look, I can take the inverse. I get three of them. I can see three NAND gates here. That's wonderful. I can just start building with those. And then I realize I have a 3-input NAND, not a 2-input NAND, a 3-input NAND. Oops. And now how do I do that? Well, there are a couple different ways to do it, but one of the concepts is you build effectively an AND gate that then you AND into one of the terminals of a NAND, and you get a 3-input NAND, and as a result. Works fairly well, and so you just end up making an inverter out of that. And so therefore you can do this. And by the way, this function is an interesting one because it basically gives you a 0 if I have 0 or 1, 1, or a 1 if I get 2 or 3 ones. So it kind of almost counts. It's kind of an interesting function and used in a lot of interesting places. So it's just kind of interesting property to see these different functions and how these kind of work out.